Okay, we'll go ahead and get started with some introductions for the webinar. And as people roll in, we'll just keep going, okay? So hello everyone, my name is Sarah Argo and I'm the marketing specialist here at Photosound Technologies. I would like to take a minute to thank everyone for joining us for today's webinar over fiber tube tracking with photoacoustic imaging by using the Legion amp. We will have Samuel Toler, our system test engineer, briefly discussing the Legion amp system overview and a few of the possible applications with the Legion amp. And then we will move into a pre-recorded demonstration with the Legion amp presented by Dr. Jan and Mr. John, who are part of Dr. Mohammed's lab at Wayne State University. Throughout the presentation, if you have any questions, please enter them into the Q&A area on your screen, and we'll address them at the end of this webinar. And at this point, I'd like to hand it over to Sam.
Thank you for the introduction, Sarah. Hold on, let me get this going. Okay, so also a big thank you to everyone who is tuning in now. I'd like to start talking about ultrasound systems as well. Ultrasound acquisition systems, they typically function with a single frequency emission source, and they receive on a targeted frequency. And on the other hand, photoacoustic data is by nature broadband and therefore requires a broadband acquisition system. So our Legion amp is a broadband analog front end that can interface with typical ultrasound and photoacoustic systems, including the Verisonic system. And this will improve your signal to noise ratio and your low frequency response as well. So to accomplish this, our Legion amp is designed with a high input impedance rather than the default 50 ohms of many systems. On the slides here, the top two graphs depict a simulated model of photoacoustic signal data from two different sized spherical sources. You can see that an analog front end with 50 ohm impedance, it's in blue here and blue here, if you can see the mouse. The 50 ohm input impedance will have distortions that are particularly noticeable for larger sources. And with that, you'll lose part of the signal that is necessary for quantitative analysis. And with a high input impedance analog front end, you'll have extended lower frequency detection with much more minimized signal distortions. All right, apparently I have to take control of the screen again real quick. Hold on. Okay, so let's see if you can see the mouse now. All right, cool. So then that's the blue there, and then the blue here. And you'd expect to see the end tooth weight. Okay, on the bottom half, we have an example of a strong photoacoustic signal. We've got a 0.1 millimeter blood vessel, and it's being excited by 4 millijoules per square centimeter of laser energy. And it's got a mu sub A of 5 inverse centimeters and a Grunew's-Line of 0.1. This 2 kilopascal wave will propagate over 65 millimeters, resulting in a 55 pascal pressure wave. And then it will have to be converted through the transducer to voltage. And ultimately, it requires 60 dB or 59 dB to scale to the 2-volt range of our Legion ADC. And this is for a strong source. Conversely, for a small pool of contrast agent, you would need 100 to 1,000 times greater amplification, which we highlight here. All right, now I'm trying to switch to the next slide. Okay, cool. So this block diagram here is a simplified model with a probe and an amplifier and an ADC. It's got the 2.2 mega ohm or the 50 ohms that were mentioned in that previous graph, as well as the different capacitances on the probes. And this is got a 50 ohm output impedance to this ADC, which is just like our Legion amp. It's the 50 ohms is standardly used, so you won't have any sort of impedance mismatch there. So the bandwidth of our Legion amp is 25 kilohertz to 45 megahertz, and then our amplification is a flat 40 decibels. On the bottom two graphs, they were also simulated by this block diagram model. And you can see here with the low input impedances, you'll have a nonlinear amplitude response. See these here, the two blues. And that nonlinear response will result in significant distortions and loss of that quantitative information that you want if you want to do molecular or anything else. And this is the response curve that you'd get if you just had the Verisonic systems on its own. Conversely, you have a nice, really flat response rate with the Legion amp with its higher input impedance. And it goes all the way down to some very low frequencies. And this also carries over for the noise spectrum here. And you can see here the yellow and the blue are going to be the lower input impedance, the 50 ohms. And you'll just end up with a much greater signal to noise ratio since you don't have all of that noise to deal with. So now this is a demonstration of the noise levels of our Legion amp. And here we use a test board to connect our Legion amp and then measure noise spectral density. And on the left, we have a hand close to an open connector. And on the right, we've got a hand close to a closed connector. And this connector has about a meter or so cable going to a probe. On the left-hand side, you can see the baseline noise level without this probe connected is around the same noise level as a 50 ohm resistor. And so it's 0.9 nanovolts per square hertz is the 50 ohm resistor noise level. And then on the right side, you can see there's a baseline shift from the probe being connected, and that's just the characteristics of the probe itself and the noise that it produces. And then you can also see here on the left graph, you can see the response of EMI pickup due to my hand being present to very closely to the connector. It's not touching. And then on the right-hand side, these spikes here are actually not from my hand, and I can point that out in the next slide as well. So. And then here on these top two graphs, this top right one is the same from the previous. And then the top left one is without the hand being close by, and you can see the same spikes here. And then the bottom left is just with the system powered off for control. And then the bottom right is no probe connected, no hand present. You can still see some conditions in our lab that do cause some EMI pickup with these discrete spikes here. So let's see. All right, our Legion amp has two different configurations. It includes a standalone version that can be used with other systems, including the Verisonics Vantage. It's got the zero insertion force handle. It's got these two adjustable standoffs for strain relief or stress relief. And then it also has these, the Legion amp also has other configurations, which are for our Legion ADC. It has Samtech connectors on the other side of these boards, and you can connect them to your own ADC if it has that style connector, and you can work with us and we can see if it works. But these are just some of the options that we do offer, and we're constantly trying to improve these. This QLC 260 board, it now has metal shielding around it just to hopefully catch more of that EMI and send it to ground instead. So this concludes my introduction to the Legion amp. It's a 128 non-multiplexed parallel channel amplification analog front end. So I hope from this that you can see that our Legion amp will increase your signal to noise ratio as well as low frequency response, which is the first step towards performing quantitative analysis of your photoacoustic data. So now on to Wayne State for some applications of the Legion amp. Oh, hey, Dr. Yan, it appears you're still muted.
Oh, hi. Hello. Sorry, I didn't notice I was muted. Hello, everyone. Good evening and good morning. I know you are from all over the world. And I am Yan, a postdoc in the Photoacoustic and Ultrasonic Research and Engineering Lab at Wayne State University. My PI is Dr. Mohammad Mehrmohammadi. Our lab aims to develop novel hybrid ultrasound-based diagnostic method and define their clinical utilities. For example, we develop novel multi-parametric transvaginal system to evaluate preterm risk, and endoscopic ablation system for early diagnosis of cervical cancer and treatment, a foreign photoacoustic and ultrasound system for detecting breast cancer. Also for today here, my colleague Samuel Zhang and I will show you some of our research about photoacoustic guided fiber tip tracking using Legion M. Zhang will introduce the project, and I will show you a real-time demo using the Legion M. Now, please welcome my colleague, Mr. Zhang, to introduce the project. Zhang, you are muted.
Yeah. Hi, everyone. My name is Samuel Zhang. I am a fourth-year PhD candidate working in the same lab in the field of biomedical engineering. So going on with the introduction. In today's world, laser ablation plays a major role in various clinical procedures, including nerve stimulation, dermatology, tumor treatment, and cancer therapies, and removing varicosities in diseased veins. Precise laser ablation treatments require the accurate placement of the ablation catheter tip within the diseased tissue and monitoring the real-time temperature variations during the procedure. Ultrasound imaging is the gold standard imaging modality which enables surgeons to visualize the catheter within the diseased tissue. However, ultrasound imaging artifacts, including angular dependency caused by the catheter transducer misalignment and the placement of the catheter in angle veins, limits the catheter tip visibility. So if we can see, the image on the left shows the accurate visualization of the ablation fiber within the diseased vein, but due to angular dependency towards the middle, we can see that the fiber tip is not clearly seen. Other artifacts, including acoustic shadowing, reverberation, limits the catheter tip visibility in deeper tissues. As we know, ultrasound imaging reveals the anatomical structure of the background tissue. Photoacoustic imaging is a hybrid imaging modality which uses pulse laser excitation to probe the optical properties of the tissue in the form of acoustic waves as a result of thermoelastic expansions occurring within the tissue. In short, PA imaging visualizes the functional properties of the tissue of interest. Since both modalities utilize an ultrasound transducer to acquire acoustic waves, the ultrasound and PA images are naturally co-registered and provide combined information about the tissue of interest. Figures 2A and B illustrate a PA-guided laser ablation system which we have developed in our lab, in which the pulse laser for PA imaging and a high-powered continuous wave laser for tissue ablation was combined using dichroic optics into a single ablation catheter. Currently, our PA-guided laser ablation system uses a relatively high-energy pulse laser system for visualizing the catheter tip using PA imaging in deep tissues. The focus of the study is to use low-energy laser pulses for visualizing the catheter tip using PA imaging in deep tissues. As explained earlier, our current studies, the normalized PA image on the left reveals a poorly visualized catheter tip with a relatively low SNR. Hence, in order to boost the signal, we use the Legion M for amplifying the PA signals at the catheter tip and minimizing the background noise in the image. The image on the right indicates an enhanced PA image using the Legion M with a higher SNR and improved visualization of the catheter tip. For evaluating the utility of the Legion M for deep tissue PA imaging, an abdominal tissue mimicking phantom was used. An ablation catheter carrying laser pulse energy of 10 microjoule was embedded within the tissue at an imaging depth of 35 millimeter, seen on the right-hand side photograph. The entire phantom was placed within an imaging container filled with water. Sagittal US and sagittal ultrasound and photoacoustic images were acquired using the ultrasound transducer. Now my colleague Yan will be walking us through with a demo and demonstrating the utility of the Legion M for deep tissue PA imaging and also the qualitative results of the Legion M.
Here is our experimental setup for the live demo. A low energy pulse laser was coupled to an ablation fiber running at 10 Hz. The input energy is controlled by about 10 microjoule per pulse. A commercial ultrasound probe, as mentioned, was used to acquire the ultrasound and Photoacoustic image. A motorized pulling system moves the fiber with a constant speed of about 5 millimeters per second. The ablation fiber was placed about 3 centimeters inside the tissue. Coverage of the ultrasound and Photoacoustic image were acquired at 10 frames per second. Here shows our use case of the Legion M. It is very easy to install in my personal view to the Ultrasonic system. The button supports stabilize the device while connecting the ultrasound probe. Okay. The connection of the ultrasound probe is as easy as it is to connect to the, sorry about this. The video is not played correctly in my end. Yeah. So it's very easy to connect it, and it's as the same as we connect to the ultrasound machine. And on the top, you can see while the system is running, there is an indicator shows the system is running. In the software part, the Legion M is also user-friendly. We only need to create a new transducer type for our use case, which is exactly the same as the original definition in Ultrasonic, but changes the connector pin number. The pin number table can be found in the user manual. This slide shows the experimental result of the live demo. The left panel is the ultrasound image. From this video, we can only visualize some movement about 27 millimeters. However, we cannot distinguish the ablation fiber, let alone the fiber tip. The middle panel shows the PA images. A very low PA signal will detect, if you can see here, is very low signal, which only identifying the fiber tip. Since the pulse energy is very low, about 10 microjoule per pulse, which gives us a fluence about 1.3 millijoule per centimeter square. As purity is shown, is 4 millijoule per centimeter square. So you need about 60 dB to amplify the signal. You can think 1.3 millijoule probably need 100 dB to amplify the signal. The signal is harder to visualize in these non-normalized images. But in contrast, in the right panel shows the amplified PA images with Legion M. A much better visibility of the fiber tip can be demonstrated. Now my colleague John will walk you through more quantitative analysis of our result.
Okay, moving on to the quantitative results. For the same pulse laser energy of 10 microjoules, the PA image enhanced by the Legion amp indicated a higher SNR and more improved cathetative detection when compared to the PA image acquired without the amplifier. Also, PA images acquired without the Legion amp revealed an SNR 3 times lower than an enhanced PA image. The Legion amp enhances the SNR of the PA image by 3 times than that of an unamplified PA image and potentially minimizes the background noise in the image. Also, the amplitude of the amplified signals are 10 to 40 times stronger than the original unamplified PA signal. Hence, the Legion amp can be used for low-energy PA-guided cathetative tracking in deep tissue-based clinical applications. In addition to cathetative tracking, real-time temperature monitoring is also crucial for precise ablation treatments. In PA imaging, the amplitude of the PA signal is directly proportional to the relative changes in the ambient temperature. PA imaging provides non-invasive, localized, real-time thermometry about the tissue during ablation procedures. Utilizing the Legion amp to monitor real-time temperature variations in deep tissues will be the focus of our future studies. Thank you.
Thank you, Samuel, and Jan for that. At this point, At this point, we would like to launch the audience poll and get a little more information about whether or not you would like additional information regarding the system. The poll should be able to be seen now on your screen. There are a few different options, and we'll be happy to reach out and talk more about research needs you may have. If you are looking for any additional information, or if you're here to learn about new and interesting technologies, that's okay as well. I'll give everyone a few minutes to reply, and at this time, please also make sure you're entering any questions that you may have in the Q&A portion, as we will move to that portion next. Give it about 30 more seconds, and then we'll move to the Q&A portion. Okay. At this time, I'm going to go ahead and close the audience poll, and we'll move to the Q&A portion. Okay, so these questions can be for our colleagues at Wayne State or for Samuel, depending on what your questions are. So we do have one. It says, can this be used for thermoacoustic imaging as well? Sam, would you like to explain?
Sure thing. So yeah, so it's within the same bandwidth, the 25 kilohertz up to the 45 megahertz, and if that's your signal that you're trying to analyze, you should be able to pick up these signals as well. Me personally, I'm not an expert on thermoacoustic imaging, but you know, that's I could maybe get more information on that too later if you'd like. I could probably email it to you.
Give a few more minutes to see if any questions roll in. Okay, there aren't any questions so far, just the one. Okay, at this point, we're going to move on from the Q&A session. If there are any further questions, please feel free to still ask them as we conclude the end of the webinar and give closing remarks. So Photosound Technologies excels in research, development, and manufacturing of specialized equipment for biomedical applications based on photoacoustics, ultrasound, and molecular imaging. Here are a few of our other products that can be found, ranging from imaging platforms to OEMs, and all of our products can be found at www.photosound.com. And at that, we will conclude today's webinar over the Legion amp and fiber chip tracking with photoacoustic imaging using the Legion amp. I'd like to give a special thank you to our colleagues at Wayne State and to Samuel Toler for taking their time to present this. We have one more question before we finish, or two. It says, can this be used in brain imaging? I mean, through the skull. Sam?
So I am aware that there is a use of the Moleculus, our ultrasound and photoacoustics imaging system, and they're doing mouse brain stuff related to that. So I do believe so. It would depend on your imaging modality as well, and how you're gonna, you know, get the signal in and get it out. And so yeah, I hope that answers it. Yeah, we can send you further information about that. Actually, we might have. You know, we should probably see what studies are available, and we can maybe send that your way too.
Yes. And then the next question is, when will the next webinar about Photosound products be? We're hoping to host our next Legion AMP webinar in the end of May, or if not in June. As soon as that date is confirmed, I'll make sure to let you know. But right now it is scheduled for late May, early June. Okay. If you have any further questions, please feel free to reach us out to us at info@photosound.com, which is right here, or visit us at our website at www.photosound.com. For any questions pertaining to this study, you're more than welcome to email Dr. John or Mr. Samuel John. They'll be happy to answer any questions relating to the study.
Yes, actually, I saw there is a question asked in the chat from Dr. Avanaki. Is asking how can noise is not amplified while the signal amplified?
Yes, yeah. So the noise is there's two sections of this that you'll have to think about. So you have the length of cable from the probe to the connection to the amplifier, and that length is going to be picking up any sort of EMI, and it's going to have the noise associated with the probe itself, and that noise will get amplified. But following the amplifier, there's no, like, that 40 dB of amplification isn't going to occur, and it's not going to be as big of an issue. So once you've amplified your signal, and as long as your probe is really well shielded, you'll be okay. And that's how, like, you get the better signal to noise ratio, because basically you're not picking up any noise from that front portion, which is the most critical for shielding. Background signal versus desired signal. Yeah, so the background signal is, once again, it's dependent on your shielding. As far as like electrical noise goes, or thermal noise from the electronic components, that's what that baseline noise level is. That's pretty much your constant white noise that you'll see, and it will be around that of the 50 ohm resistor. It's about 9 nanovolts per square hertz, and sometimes lower, as you saw in the previous things. Actually, we could probably go to it if you want, or if you want me to send you more about that too, I can. But basically, any EMI will be picked up if you don't have good shielding. So that could be some background noise as well, and that's dependent on how well your probe is insulated from electromagnetic interference.
If you would like to go back to the slide, Sam, you're more than welcome to.
Oh, of course, yeah.
Yeah,
Let me take over. I'd like to show you, because it's interesting. Okay. And this is important because it is a big, a common source of questions is coming from noise sources, and like, hey, I've got this noise here or this noise there, and oftentimes if it's intermittent, it's likely electromagnetic interference, and if it's like a rather static noise you're constantly seeing, then that's probably some sort of thermal noise, unless it's like at the very, very low end of the near field. Then it would be different. So here on these slides, we have, this is with the probe connected, and you can see this baseline noise here is what you just see all the time. That would be background noise, if you will. But then you can also have these spikes at multiple different frequencies, just depending on whatever electromagnetic interference. If you have some labs next door, above, below, sometimes, like, I know, like, surgical lights can even cause noise spikes, and you have to kind of, it's really hard to troubleshoot those kinds of things. So when you do experience something like that, you'd want to, like, change locations and try turning certain things off. But ultimately, you want to have this probe be really well shielded, and then you also, the cable length, you want that to be nice and short. The shorter the cable length, the lower the, or was it the higher the resonant frequency, and so you can get that range out to outside of your frequencies of interest. So yeah, all right. I hope that sufficiently answered it.
Okay, and at this point, we would like to conclude the webinar. Thank you everyone for joining us today. If you have any questions, please feel free to reach out to us. And thank you again to our colleagues, and we hope to see you all at the next webinar. Goodbye.